Let's do a very simple example. Suppose v1 and v2 are these two vectors. That says that this subspace W is the xy plane. And the way you project a vector x, y, z, find the closest point in the xy plane, is you simply set the z coordinate equal to 0. And let's see how that works with the formulas we just had. So A is this matrix 1, 0, 0, 0, 1, 0. And A transpose A, if you just compute it in 2 seconds, you'll see you get 1, 0, 0, 1. So that's K, and so K is the same thing as K inverse, is the identity. And this V star that we were looking for turns out to be A times the identity times A transpose times x, y, z. Well, A transpose is the matrix 1, 0, 0, 0, 1, 0, 0, 0, 0. That's A transpose, which is a 3 by 3 matrix. And when you apply it to x, y, z, you get, of course, x, y, 0. As simple as could be. Okay? Let's do one more example like that for review. Let's take these two vectors, v1 and v2. So they have the same span, which is the xy plane. So I'm really redoing the same problem, but with a different basis of w. And we have to be getting the same thing. xyz goes down to xy0. But let's just run through the calculation quickly and see how that works. So A is 2, 1, 0, minus 1, minus 1, 0. And this matrix K turns out to be 5, 1, 1, 2. So K inverse is 1/9, 2, 5, minus 1, minus 1. And this x star that we were talking about, which is to say K inverse A transpose times xyz, turns out to be 1/9, 3x plus 3y, 3x minus 6y. This is a 2 vector. And then the v star that we're interested in is A times that, which is to say 2, 1, 0, 1 minus 1, 0, applied to this thing. And what you get is 1/9, 6x plus 6y plus 3x minus 6y, followed by 3x plus 3y plus 3x, minus 3x plus 6y, 0, which is 1/9, 9x, 9y, 0, which is to say xy, 0. Okay, so again, that's just review. I went through that kind of quickly, but we've done a bunch of these. So now let's go on and look at the new formula. Let's move on to the new method of doing these kinds of calculations, and that's using what's called orthogonal projection. So what is that? Well, the setting is a vector space V with an inner product and a subspace and a vector. And I'll draw the picture over here in 2 dimensions. Suppose the subspace looks like this. This is W, and this is V. The orthogonal projection of V is the following. You draw a line from V to the plane, which makes a right angle. That's the key orthogonality condition here. That's a right angle. And the orthogonal projection is this vector W. So let's write down the definition. W, the orthogonal projection of V on the subspace W is the following vector. Well, it's the this is V and this is W, so this is V minus W. And the condition is that V minus W is supposed to be orthogonal to the subspace. So it's the following. It's the vector W which satisfies V minus W. W prime is equal to 0 for all vectors W prime in W. So you have to test that it's in fact orthogonal to all of the vectors in W prime. In this example, there's essentially just one vector W prime. But of course, in general, if you had a two-dimensional subspace, you have to take all the different vectors W prime, and you have to check that this V minus W is orthogonal to all of them. And of course, if you think about it, it's enough to check this for W prime running in a basis of the subspace W. By the way, any basis of W, doesn't have to be an orthonormal or orthogonal basis or anything. As long as it's a basis of W, then you're in good shape. Before I go on, let me just make one comment. So what we were doing before was we had the following picture. We had a vector V, and when I was looking for the closest point, what I was looking for, I'm changing notation slightly here, but I looked for the point W such that this distance was minimal. On the other hand, what I'm doing now, given a vector V and a subspace W, I'm looking for the orthogonal projection, which makes this a right angle. And I think it's pretty easy to see that, in fact, these two things are the same. That is to say, if you pick the point which is closest, that is given by taking this to be a right angle. And that's just to see that is easy. It's the triangle inequality. So that's why what we're doing now is the same as what we're getting the same. The answer is what we were doing before. We're just thinking about it differently in terms of the orthogonal projection. Okay, so the nice thing about thinking of it in terms of the orthogonal projection is there's a nice formula for it. So remember, we're given a subspace W which has some basis, and well, we're free to choose an orthonormal basis. So it doesn't matter what basis you use, so choose an orthonormal basis. So typically, you might choose that by doing Gram-Schmidt, but it doesn't matter. However you come up with an orthonormal basis is fine with me. Once you have an orthonormal basis, then what is this orthogonal projection? You start with a vector V, and this vector W is the one which is supposed to satisfy V minus W, is supposed to be perpendicular to all of the vectors in the subspace W. Well, since the UIs are a basis, it's enough to check that it's perpendicular to all of the UIs, and the result is very simple. So what is this W? W is some C1U1 plus ... CMUM, and you're supposed to tell me what the CJs are, and the answer is W is equal to the inner product V U1 plus ... V inner product UM times UM. In other words, CJ is simply V inner producted with UJ. So that's an extremely nice formula. And in many ways, it's much easier to use than the ones we had before. So Now the cost is that you have to come up with an orthonormal basis instead of an arbitrary basis, but that's not so bad by Graham Schmidt. That's fairly straightforward. Okay, so why is this true? Why is it true that the coordinates of the UIs of this orthogonal projection are simply these inner products? Well, let's see. Let's go on to the next slide for that. Okay, so why is this true? Here's what I'm saying. You take your vector v, and I'm claiming that if you take w to be this sum that I mentioned on the previous slide, where you add up the uj's with these coefficients, that v minus that w is perpendicular to uj for all j. Why is that true? Well, suppose you didn't know that. It's actually sort of easier to think of it this way. We know that w is some vector u1, c1 u1 plus dot 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 cm um for some ci's. And for some CJs, I'm calling. What is CJ? Well, let's just write down the condition that V minus W be perpendicular to UJ. Well, that is to say, V minus C1 U1 minus dot 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 CM UM is supposed to be perpendicular to UJ, which is to say this is supposed to be 0. So here I just plugged in this for W. And what is this inner product? Well, this is equal to V uj minus C1 U1 uj minus dot dot dot, and you get all of these ui uj's, and at some point you get cj uj uj, and that's supposed to be 0, and all of these terms are 0 except for this one where you pair uj with uj, in which case this is 1, and you get that v uj minus cj is equal to 0, and that's what I was claiming. Cj is equal to v uj. Which is this formula right here. So it's quite simple. Okay, let's do an example. Suppose u1 was this vector and u2 was this vector. So let's check. These two vectors are orthogonal and they have length 1, so this is an orthonormal basis. And the space that they span is, again, the xy plane. So we're doing this problem for yet a third time. And let's see what happens when you project the vector v onto this plane. Well, what you get is the vector w, which is v u1 u1 plus v u2 u2, and let's see, vu1 is x plus y over radical 2 times the vector u1, and then you add, let's see, vu2 is x minus y, excuse me, there's a square root there, so you get 1 over square root of 2 x minus y times 1 over the square root times the vector, which is 1 minus 1, 0. And let's see what that comes out to be. Unless there's a contradiction in mathematics, it should look familiar. So this is 1/2 x plus y 0 plus 1/2 x minus y plus x 0. And what is that equal to? That's 1/2 x plus 1/2 x, and the y's cancel. And that's y, excuse me. This is minus x plus y here. the y's add and the x's cancel, and you get y 0, which is what we saw before. So, all right, that's a quick example of that. And let's generalize the theorem just a little bit. Instead of having an orthonormal basis, suppose I had V1 through Vm were orthogonal, not necessarily orthonormal, and W was the span. And if you take a vector V and you do orthogonal projection to this subspace and call the vector W, the formula for W is what? Well, let's see. Before it was you take V and pair it with V1, and it looks like this. If they were unit vectors, this would be the answer, but they're not unit vectors, so it must be that you're supposed to divide this by length of V1 squared and so on up to length of Vm squared. And the proof's essentially the same. It's barely different. I won't bother proving it. So this is quite a handy formula. It's often convenient not to have to normalize an orthogonal basis. If you have an orthogonal basis, you can just use it, use this formula, and you don't have to normalize it. Okay, so let's go on to look at least squares and curve fitting. We talked about this back in a couple of sections ago as an application of the problem of finding the closest point to a plane. And now we're going to revisit that using orthogonal projections. So the setting is we're given a bunch of points t1, y1 up to tm, ym, and these are some measurements. And we're trying to find a curve of degree, say, k, or possibly less than or equal to k, which fits the data as well as possible, and it's the least squares fit. So remember the way we did this before is we looked at this matrix. We put 1 here, T1 down to Tm. If we were just doing a linear fit, that's what we'd use. If we were doing a quadratic fit, we'd put in some squared terms and so on. And we're trying to do a degree k fit, so we write down this matrix. And we think of this matrix as a map from R k plus 1 to Rn. And the image of it, the range of it, I should say, A applied to Rk plus 1. If you call this W, this is a subspace of dimension k plus 1. And the picture is we're given the vector y, which we write as y1 through yn, and we want to find the distance from y to w. So that's a reminder we did this already, and if you want to refresh your memory, go back and look at section 4.4. And now we're going to do this essentially the same thing, except we're going to use orthogonal projection to do the last step to compute the distance from this y to the subspace W. So W is spanned by these vectors. So I'm going to give those names. Let's let T0 be the vector of all ones. And let T1 be the vector of the t's. And so on. T2 is the vector of the T1 squareds. Okay, so up to T m, that's m plus 1 vectors, excuse me, k, up to tk. So that's the k plus 1 vectors which span W. Okay, so we have this subspace W. It's spanned by these vectors t0 through tk. There's k plus 1 of them, so the dimension is k plus 1. And remember, each, I'm just reminding you here, each ti is t1 to the I, dot, dot, dot. Tm to the I is an m vector. And it's convenient to renormalize the inner product on Rm by dividing by m. So set this to be equal to 1 over m summation vi wi, running from 1 to m. So this is just a normalization here, this 1 over m. That doesn't really change anything. It doesn't change orthogonality, is the main point. And now the problem is, well, the point is, of course, that these t's are not an orthogonal basis. So we have to apply Graham-Schmidt to this basis. And to simplify this, I'm going to assume that the ti's are all spaced equally and symmetric about 0. Symmetric around 0. So, for example, the ti's could be minus r plus 1 dot 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 0 up to r. So the spacings are all 1 and it's symmetric. You have r and minus r. So you might as well assume this is the situation. And that just simplifies some of the calculations. So what we're going to do is I'm going to define some polynomials now, q0 of t, q1 of t, and so on. And they're going to be corresponding vectors q0 and q1, and so on. And these vectors are going to be orthogonal. And what these vectors are the way you're going to get the vector q0 is you're going to take the polynomial q0 and evaluate it at t1 through tm. And similarly for each of these. So there's sort of two things going on here. There's the polynomials and there's the vectors, and you can go back and forth between them. So how do we find these guys? Well, q0, I might as well take that to be the original guy, t0. And then q1, of course, is going to be the vector t1 plus some constant times t0, and q2 is going to be t2 plus some constant times t0 plus another constant times t1, and so on, the usual Graham-Schmidt business. And the key fact is that this assumption makes this inner product T I T J equal to 0 if I and J are opposite parity. So, for example, T0 paired with T1 is 1 over m times T1 0 plus T1 plus dot 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 TR, and excuse me, TM. And by this the symmetric condition, this sum is equal to 0. So that's the basic idea. And what that says is that kind of like the Legendre polynomials, they alternate. The Q1 is not going to involve T0, and T2 is not going to involve T1. Okay, well, let's just write down the results. So I already mentioned that the vector Q0 is just T0, and Q1 is just T1. And what's Q2? Q2 is T2 minus some constant times T0. And it turns out that this constant is the following. It's what the book writes as T squared bar, which is the average of the T squareds. And I'll just write down one more. Q3, it turns out, is T3 minus T to the fourth bar over T squared bar times T1, where T to the fourth bar is similarly the average of the fourth powers. Okay? And the conclusion is that you get kind of a nice formula for the best fit polynomial. The best fit polynomial of degree less than or equal to k is the following. It's a0 q0 of t plus a1 q1 of t plus dot 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 a k q k of t, where a j is the inner product of q, this vector qj that I wrote down, with the target vector divided by the length of qj squared. And each qi, q0 of t is function 1, and q1 of t is just the function t, dot 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 qj of t is the function t to the j. Okay, so I skipped a couple of steps in here. You might want to see pages 262 and 263 for a little more details, but let's just wrap this up with an example. I apologize, this video has gone on for a pretty long time, but this least squares stuff is incomprehensible without an example, so I want to get through an example before I stop. So here's the example. We're given 3 points, -1, 0, and 1, and these satisfy the conditions. They're evenly spaced and they're symmetric around 0, and the observed values are 3, 1, and 1. And I'm going to let you in on a little secret here that there's an exact fit for this function, which is 1 minus t plus t squared. So that's the answer that we're looking for. So let's see. Let's go through the algorithm. So Q0 is this vector 1, 1, 1. And Q1 is this vector T1, T2, T3, which is to say -1, 0, 1. And now Q is a little more interesting. It's T1 squared, T2 squared, T3 squared, minus, you get the average of the squares. times the vector 1, 1, 1. This is the sort of correction vector. And see the previous slide for this, where that came from. And so that is equal to 1, 0, 1 minus 1/3 times 2 times 1, 1, 1, which is to say 1 is 2/3 is 1/3 minus 2/3 1/3. Okay, so that's Q2. And I'm going to need the lengths of these guys, so let's write these down. Length of Q0 squared is 3. If you dot with itself, you get 3. But remember, we're dividing by 3, so that's 1. And the length of Q1 squared is the sum of these guys squared, which is 2. Divided by 3 is 2/3. And the length of this fellow is, well, it's the sum of the squares, which is to say 1/9 times 1 plus 4 plus 1 is 6. Divide by 3, which is to say 6/27, which is to say 2/9. Okay? So now we can go ahead and compute A's. A0 is Q0y. And of course, I should have written y up here as the vector 3, 1, 1. So this is equal to Q0 paired with y gives you 3, 4, 5. And you've normalized, so it's 5/3. 5/3. Now, that makes me a little nervous because up here, the constant term is 1, which is certainly not equal to 5/3. But anyway, never mind. Let's forget about it. Let's just go on. What's A1? A1 is equal to Q1y over the length of Q1 squared, which is, let's see, Q1 is here. You pair this with y, you get minus 2 over the length of Q1 squared, which is 2/3. And you're dividing by 3, and you put it all together, and you get minus 1. And finally, what is A2? A2 is Q2y over the length of Q2 squared, which is, let's see, what's Q2 y? It's the inner product of this vector and this vector. It gives you 3 times a third is 1. Minus 2/3 plus 1/3. Divided by 2/9, and also multiplied by 1/3. And let's see, 1 minus 2/3. This is 2/3 over 2/9 times 3. That's 2/3 over 2/3 is 1. Okay, so, whoops. Lost my video. There we go. Sorry about that. All right, so let's write down the answer. I'll try and squeeze it here on this slide. So the degree 1 or the degree 0 approximation is just A0 times this function Q0, which is the constant function 1. So this is just the constant function 5/3. And then F1 is, well, it's 5/3 plus A1, which is minus 1, times Q1, which is the function t. So that is to say it's 5/3 minus t. And notice one of the really nice things about this algorithm is when you go to compute the next higher degree, you don't have to redo anything you've done before. The lower terms are the same, and you just add the next one. And here's the punchline. F2 is therefore 5/3 minus t plus A2, which is 1, times Q2. And what is Q2? Q2 is t squared minus 2/3. That's this guy right here, 2/3. And what is this? Well, this is sort of the key point here, which is that this f2, it's not just t squared, it has a constant term in it. And what you get is 5/3 minus 2/3 is 1 minus t plus t squared. And that's exactly correct. So, what's the moral of the story? The nice thing about this calculation is that you can, each degree builds on the last one. If I wanted to compute f3, I would just take f2 plus a3 q3, and I don't have to redo this. I just need to compute this a3 and this q3. And, of course, I don't need it in this example, but all right, that's a good place to stop. See you in class.